Hi y'all, Professor Barber here. In this lesson titled Rational Functions, we'll learn some common characteristics of rational functions, including how to find vertical, horizontal, and oblique asymptotes, and then use them to help us draw their graphs. To that end, upon successful completion of this lesson, you will 1. Be able to find vertical and horizontal asymptotes of rational functions. 2. Be able to graph those rational functions. 3. Be able to perform transformations of the basic graph y equals 1 over x. 4. Be able to simplify rational functions. 5. Be able to find slant or oblique asymptotes of rational functions and determine their end behavior. And finally, 6. Be able to solve applications involving rational functions. Roman numeral 1, rational functions. A rational function is a function of the form r of x equals p of x divided by q of x, where p of x and q of x are both polynomial functions having no common factors. The domain of a rational function consists of all real numbers x except for those for which the denominator is 0. Consider the function f of x equals 1 over x. That is your basic reciprocal functions, and from what we know about numbers, we know that for the domain, x cannot be 0, because that would give you a 0 in the denominator, and that would make it undefined. But let's see what happens if we get real close to 0. We have the statement x approaches 0 from the left. The mathematical notation is x arrow 0 superscript negative. All that means is you're going to get real close to 0 from the left of 0. So let's see what happens if we evaluate negative 1/10 in the function f of x equals 1 over x. Since it's a reciprocal function, this will give us negative 10. Okay. Let's look at negative 1 over 100. Again, reciprocal function. That's negative 100. And the last number to try, negative 1 over 100,000, is negative 100,000. Before I plot any points, I'd like to observe that at x equals negative 1, the function value is just negative 1. So if I were plotting points, I might start with negative 1, and just observe that as closer as you get towards 0, the function appears to get real close or real big in the negative direction. Let's try for going to 0 from the right side, okay? And so we're going to get real close to 0 without actually hitting 0. In the reciprocal function, 1 divided by 1/10 is 10. 1 divided by 1/100th is 100. And for the last one, 1 divided by 1/100,000th is, positive 100,000. We note in the function that if you evaluate it at 1, the output is 1. So if we were plotting points, we would start at 1, 1, and note that whatever you're doing, the closer you get to 0, the bigger that number gets. Okay? And so if we were using notation, we might say that as x goes to 0 from the right, the function appears to get to positive infinity. And if x approaches 0 from the left, the function approaches negative infinity. There's a split. So continuing with that exercise, let's get a definition. The line x equals a is a vertical asymptote of the function y equals f of x if y approaches positive or negative infinity as x approaches a from the left or from the right. So, what is the vertical asymptote of this function? The vertical asymptote is, we learned, x equals 0. That means the function can't ever be 0, but we can approach it from either side. Okay, so we previously determined that x cannot be 0, but let's see what happens if if x gets increasingly large or increasingly small. Let's begin with x approaches negative infinity. What that means is your number is going to get greater and greater to the negative. Let's evaluate. At x equals negative 10 and the reciprocal function, it'll be negative 1/10. If x gets even more negative, like at negative 100, it'll be negative 1/100. And at negative 100,000, it's negative 1/100,000. If you were to write this in decimal form, you'll see that each of these numbers get increasingly closer to 0 from the negative. And then let's go positive infinity. So what happens if we evaluate the function at 10? Well, that's 1/10. Okay, that's pretty close to 0. How about if you go further out positive, then you'll get 1/100. That's even more closer to 0. And if you do it 1/100,000, you'll get if you evaluate it at 100,000, then it's 1/100,000. And for all intents and purposes, you're approaching 0. Let's see what this means. What this is saying is, again, we'll start at negative 1. The function is negative 1. But we find out that the bigger the x gets, the closer the function gets to the x-axis. Okay. Similarly, if we start at 1, so the corresponding function value is 1, the bigger the x gets in the positive direction, the closer the graph gets to the x-axis. So, before we answer question part B, let's give a definition. The line y equals b is a horizontal asymptote of the function y equals f of x if y approaches b as x approaches plus or minus infinity. What is the horizontal asymptote of this function? We learned that as x got real small, the function appeared to go to 0. Furthermore, as x got real big, the function also approached 0. And so what this tells us is that the line y equals 0 is a horizontal asymptote. And so part C, sketch the graph of f of x. We've already evaluated those points, but let's go ahead and do it again anyway. At x equals 1, the function is 1, plot that. And at x equals negative 1, the function is negative 1. If we were to connect the pieces from part A and part B, we'll get the graph of the reciprocal function. Now let's observe for positive numbers. If you take some number and divide it by a real big number, the quotient is small. So think about that for a moment. That is, if you have a slice of pie, the more slices that you cut into, the smaller that piece of pie. That's the first fact statement. And the other is some constant divided by a small number is something very, very big. And so the closer you get to dividing by 0, though you can't, the bigger your quotient is going to be. Roman numeral 2, transformations of f of x equals 1 over x. That is, we are looking at transformations of the basic reciprocal function. A rational function of the form r of x equals ax plus b divided by cx plus d can be graphed by shifting, stretching, and or reflecting the graph of f of x equals 1 over x using linear fractional transformations. Sketch the following transformations of f of x equals 1 over x. Part A, r of x equals 1 over x plus 5. Let's note that for this function, r of x equals 1 over x plus 5, we have a restricted domain. That domain is such that x cannot be negative 5. And so we might write this in interval notation as negative infinity to negative 5, not including negative 5, union negative 5 to infinity. Or, more simply put, we could just write the domain is such that x cannot be negative 5. So we got the domain addressed. Now let's look at the idea of transformations. We see that r of x is actually the original function with the argument replaced by x plus 5. And when you add or subtract in the argument, that's a horizontal shift. So this tells us that r of x is the graph of f of x shifted to the left 5 units. Okay? And then I'd like to point out one more thing, and that is consider that the domain is such that x cannot equal negative 5, and that gives us the vertical asymptote. Vertical asymptote. That's the line where the graph can approach but never touch, for r of x is x equals negative 5. So in conjunction, the domain cannot include negative 5. That is the vertical asymptote, and this is also the graph of 1 over x shifted to the left 5 units. And that gives us the graph of r of x equals 1 over x plus 5. Again, let's note, here's the vertical asymptote, and that is the equation x equals negative 5. Now, along with the vertical asymptote, we are concerned with a horizontal asymptote. And this graph shows there is a horizontal asymptote, though we did not bother to get it. And that horizontal asymptote is the x-axis, or the equation y equals 0. We know that when the degree of the numerator is less than the degree of the denominator, the rational function has a horizontal asymptote of y equals 0. Sketch the following transformations of f of x equals 1 over x, part B. S of x equals the quantity 2x plus 9 divided by x plus 5. We can recall from part A or from our understanding of rational functions that 0 cannot be a denominator value. So we know that the domain of this function is such that x cannot be negative 5. That gives you a 0 in the denominator. And so we know by definition that we have a vertical asymptote of the line x equals negative 5. Let's sketch that in place. So we've got vertical asymptote equals x equals negative 5. Let's get 2 more pieces of information as we continue. The things that are always helpful when you're graphing any function is to know your zeros, and that's your x-intercepts, and also your y-intercepts, both of them if they're easy enough to find. And to find your x-intercept, using the same rules, this is where y equals 0. Now the tricky part is you can set the entire rational expression equal to 0, but your denominator cannot be a 0. So in order for a fraction to be 0, only the numerator in this instance would be 2x plus 9 can equal 0. Solving for x, we get negative 9 equals 2x, and solve for x, you get negative 9 halves. So that is the ordered pair, negative 9 halves, comma 0. And negative 9 halves is negative 4.5. So let's go ahead and mark that on the x-axis. And let's look for y-intercept. And the y-intercept is where x equals 0. So in your rational function, let's put a 0 in every place there's an x. So s of 0 is equal to 2 times 0 plus 9 divided by 0 plus 5, which is 9/5. So that corresponds to the ordered pair 0, 9/5. That's 1 4/5. So let's go ahead and plot that. We'll go to 0 and 1 4/5. So knowing the basic shape of the graph, we know that it's probably going to connect like this. We need to continue working with this to see if we can find a horizontal asymptote. One of the options we have is to perform polynomial long division to rewrite this expression using the division algorithm. So let's do that. We'll have x plus 5 as the divisor into the dividend 2x plus 9. Okay. What do you multiply to x to get 2x? 2. So we'll put the 2 above the constant 9. 2 times x is 2x, what we needed. And then plus 5 times 2 would be plus 10. Subtract, and we get a remainder of -1. So we're going to express the 2x plus 9 divided by x plus 5 using the division algorithm. We get that the quotient, the answer is 2, and you have a remainder of -1 divided by the divisor of x plus 5. We're going to rearrange this a little bit so that we can pick off the transformations. So taking that expression, I'm going to put the remainder expression first and write that as the negative of 1 over x plus 5 plus 2. Couple of things we see right away, but let's go ahead and again write this as a transformation of f of x. This is actually negative f of x plus 5, which jives with the fact that we got a vertical asymptote at -5 plus 2. That plus 2 tells us we shift up 2 units. So for the horizontal asymptote, for the function f of x equals 1 over x, remember the horizontal asymptote was the x-axis, so that was y equals 0. The shift up 2 means we take that horizontal asymptote, move it up 2 units, and actually we have a sufficient guideline to draw the graph. Let's extend what we started before. As x gets larger and larger and larger, the function value approaches 2 but never reaches it. As x approaches -5 from the right, the function value gets smaller and smaller and smaller. Similarly, we draw the other piece using the base shape. That's a horrible looking graph, but you get the idea. That's the graph of s of x equals 2x plus 9 divided by x plus 5. We also have a quick rule that gets us there. That rule states, we observe that when the degree of the numerator is equal to the degree of the denominator, the rational function has a horizontal asymptote of y equals the ratio of the coefficients of the highest degree terms. Let's observe. S of x was equal to 2x plus 9 divided by x plus 5. For the highest degree in the numerator, the number is 2 that's multiplied to the x. In the denominator, it was 1. 2 over 1 gave us the horizontal asymptote of y equals 2. Roman numeral 3, asymptotes of rational functions. Let R be the rational function R of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... plus a sub 1 x plus a sub naught divided by b sub m x to the m plus b sub m minus 1 x to the n minus 1 plus ... b sub 1x plus b sub naught. 1. The vertical asymptotes of R are the lines x equals a, where a is a 0 of the denominator. 2. Part A. If n is less than m, that means the degree of the numerator is less than the degree of the denominator, then R has the horizontal asymptote of y equals 0, which is the x-axis. B. If m equals n, that is, the degree of the numerator and the degree of the denominator are the same, then R has a horizontal asymptote of y equals a sub n divided by b sub n. That is the ratio of the leading coefficients of the numerator to the denominator. And finally, part C, if n, the degree of the numerator, is greater than m, the degree of the denominator, then R has no horizontal asymptote. Sketch the graph of f of x equals x squared minus 2x plus 1 quantity divided by x squared plus 2x plus 1 quantity. Let's begin by observing that the degree of the numerator is 2, its coefficient is 1, the leading term of the denominator is also degree 2, leading coefficient 1. So the first thing we pull off is that the horizontal asymptote is the line y equals the ratio of 1 to 1, which is just 1. So let's sketch that horizontal asymptote in place. Next, let's go ahead and factor the numerator, which would be x minus 1 times x minus 1. We could even simplify that and write it as x minus 1 quantity squared. Denominator factors to x plus 1, x plus 1, and that could also be written condensed as x plus 1 quantity squared. The vertical asymptote consists of the x values that cause the function to be undefined. So in this instance, we get that the vertical asymptote is the vertical line x equals, what makes x plus 1 equal to 0? Negative 1. So let's go ahead and sketch that vertical asymptote in place. So we have vertical asymptote and horizontal asymptote. Let's begin with the basics when graphing. Okay. We want to know x-intercepts and y-intercepts. So we found the asymptotes. That was step 1. Step 2, I'm going to look for intercepts. To find the x-intercept, you set y equal to 0. So in this instance, we're going to have 0 is equal to, and remember, when a fraction is set equal to 0, only the numerator can equal 0. So I'll take the most simplified term, that is 0 is equal to x minus 1 quantity squared, and that gives us the x value of 1. So the x-intercept is the ordered pair 1, 0. Wow, that's right on the x-axis. We'll mark that. And then let's solve for the y-intercept. The y-intercept is when x is equal to 0. So when we solve for that, you can solve it wherever you want to. I'll just put it in the original. So f of 0 is equal to 0 squared minus 0 plus 1 divided by 0 squared plus 0 plus 1, which is 1. And so that ordered pair is going to be 0 for the x, 1 for the y value, and look at that, it is actually on the horizontal asymptote. Now what we have to do next is to evaluate its behavior on all sides of the asymptote. So let's pick some select values and we will proceed. So we'll pick some values to evaluate. So I'm going to write as my set of directions, evaluate at some x's. For fun, I'm going to pick -2, and the reason I chose that is it's in that quadrant area marked off by the intersection of the two asymptotes. So let's evaluate at -2, and I'm going to use the form x minus 1 quantity squared divided by x plus 1 quantity squared, because I think that'll be the easiest form for me to evaluate. Making a t-chart for x and f of x, I'll start with -2. Okay, so -2 minus 1 is -3, and so I'm going to have the ratio of -3 squared divided by -2 plus 1 is -1. And when we square that, we're going to get 9 over 1, which is just 9. So at 2, the corresponding value is 9. Let's observe that when you're choosing negative numbers, that's x negative, okay, the numerator is always going to be greater than the denominator after you square it. And so that tells us that the quotient is always going to be bigger than 1. And so whatever we're doing, the general shape of this graph is going to be approaching the asymptotes and guide it that way. Even more interesting again is that as long as you're choosing x that's less than 0, okay, and so you're choosing negative numbers, the quotient of x minus 1 squared plus x plus 1 squared is going to be bigger than 1, and so it matches on this side of the asymptote. Now, we know that it's going to connect to this point, and what we've got to do is figure out what the graph does between 1 and positive infinity. And so let's make a few other observations. Just for fun, I'm going to pick a value of x greater than 0. And an easy one for me to pick, greater than 0, let's go greater than 1. So how about just 8? That's a big number. If we pick 8, we're going to get 8 minus 1. That would be 7 squared. Divided by, this is supposed to look like 7. And 8 plus 1 is 9 squared. Guess what? Even if we don't compute this, you know that 7/9 is going to be less than 1. And if you square a number less than 1, it's going to still remain less than 1. So we understand that this graph will probably behave kind of like this, and that's the shape of our graph. Roman numeral 4, common factors in numerator and denominator. If s of x equals p of x over q of x, and if p and q have a factor in common, then we may cancel the common factor, but only for those values of x for which the factor is not a 0. This is because division by 0 is not defined. Since s is not defined at those values of x, the graph of s has a hole at those particular points. Sketch the graph of f of x equals x squared plus 3x plus 2 quantity divided by x squared minus 1 quantity. This rational function, I begin by finding the horizontal asymptote. I will denote with h dot a dot. The horizontal asymptote is a horizontal line, so it's going to be y equals. When the degree of the numerator and the degree of the denominator are the same, the horizontal asymptote exists, and it is the ratio of the leading coefficients. So this one will be 1. Now, before we do anything else, let's factor the numerator and the denominator to see if there are any common factors. The quadratic x squared plus 3x plus 2 factors to x plus 2 times x plus 1 divided by the x squared minus 1 is a difference of squares, so we can write the x squared minus 1 as x minus 1 times x plus 1. Now, it's very tempting to, and if we were just simplifying, we could we could just cancel the x plus 1s. However, even if we do, the x plus 1 factor would give us a 0 in the original unsimplified form, so we could write this as x plus 2 over x minus 1 with the understanding that x cannot equal negative 1, because the negative 1 in the original would give us a 0 in the denominator. So let's go ahead and rewrite f of x as the ratio of, what we have left is x plus 2 divided by x minus 1, provided that x does not equal negative 1. So even in the factored and simplified form, we still have a vertical asymptote, and that vertical asymptote would be the equation x equals 1. If you substitute 1 into the simplified form or even the original form, you get a 0 in the denominator. Now let's draw the horizontal asymptote of y equals 1 and the vertical asymptote of x equals 1. So we have the horizontal asymptote and the vertical asymptote in place. Let's go back and think about what happens at x equals -1. What happens is that the graph ends up having a hole instead of a vertical asymptote. What does that look like? Well, let's evaluate it in the simplified version. So f of -1 would be equal to -1 plus 2 divided by -1 minus 1, and that is 1 over -2. What we have here is that at -1, comma -1/2, the graph of f of x has a hole. So we go to -1, -1/2, and just make a hole. Now the rest of the points, evaluate a few, and you'll be able to sketch the reciprocal function that approaches the asymptotes, remembering to leave the hole in place, and here we go. Again, if you need to evaluate some points in your original function just to make sure that you have the shape of the graph. Sketch the graph of f of x equals 1 over x squared plus 1. Let's begin by looking for horizontal asymptotes, if any exist. A horizontal asymptote would exist if the degree of the numerator is less than the degree of the denominator, and that is the case for this rational function. In fact, when the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0, or the x-axis. Now let's look for vertical asymptotes. Vertical asymptotes are where the function is undefined, and that happens for rational functions when the denominator equals 0. So now we're going to look for vertical asymptotes and look for where x plus 1 could equal 0. If we proceed to solve this, you can subtract 1 from both sides and you get x squared equals -1. Guess what? The square root of -1 is an imaginary number, and so this tells us there is no value for which, no real number for which the denominator would equal 0, so there are no vertical asymptotes. This reduces us to just having to find a couple of points. So let's make a t-chart and we'll select some points to get a general behavior of the graph. We'll have x and f of x. I'm going to begin with 0, looking for a possible y-intercept. If we put 0 in for x, I get 1 over 0 squared plus 1. And 1 over 1 is just 1, so I'll have a y-intercept. Let's pick a few points around the origin. I'm going to pick -1. That would give me 1 over -1 squared plus 1. -1 squared is +1, so this gives me 1/2. And we'll try +1, and that's going to be 1 over 1 squared plus 1, which is also 1/2. Let's plot these points. I got 0, 1, -1, 1/2, and +1, 1/2. It appears to be symmetric about the y-axis. For clarity, I'm going to pick one more point. I'm going to pick 3 and evaluate that. So we've got 1 over 3 squared plus 1. That's 1 over 9 plus 1, or 1/10. That's pretty close to 0. So at 3, it's about 1/10. It's symmetric. So we'll go ahead and plot the same value on the other side, paying attention to the horizontal asymptote. We get a graph that looks kind of like a bell curve. Sketch the graph of f of x equals the quantity 2x squared plus 7x plus 6 divided by x plus 2. I'm going to begin looking for the horizontal asymptote. Let's observe that the degree of the numerator is squared. The degree of the denominator is 1. And when the degree of the numerator is greater than the degree of the denominator, there are no horizontal asymptotes. Now, before we outright conclude that we have a vertical asymptote at x equals -1, let's factor the numerator. The numerator factors very nicely into 2x plus 3 times x plus 2. The denominator still is x plus 2. Now we can cancel the x plus 2's, but we cannot cancel the 0. So even if you do that, we have to remember that x cannot equal negative 2. So the f of x can be simplified a little bit and written as 2x plus 3, which is just a line, provided that x does not equal negative 2. So we're going to have a hole, an undefined point on the graph where x equals negative 2. Let's find that value in our simplified function. So we'll do f of negative 2 is equal to 2 times negative 2 plus 3. Negative 2 times 2 is negative 4. Negative 4 plus 3 is just negative 1. So we actually have a hole at the point negative 2, negative 1. Let's mark that negative 2, negative 1. We can graph the line f of x equals 2x plus 3. Okay? That's a line with a y-intercept at 3 and a slope of 2. So that's up 2 over 1, up 2 over 1. All we need are 2 points to define a line. And so now the rational function that's defined by 2x squared plus 7x plus 6 divided by x plus 2 is actually a line 2x plus 3, provided that x does not equal negative 2. Roman numeral 5, slant or oblique asymptotes. Recall that for the rational function f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub naught, all divided by b sub m x to the m plus b sub m minus 1 x to the m minus 1 plus dot 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 b sub 1 x plus b sub naught. If the degree of the numerator is greater than the degree of the denominator, then the graph does not have a horizontal asymptote. However, if the degree of the numerator is greater than the degree of the denominator, that is, n is greater than m by exactly 1 degree, then r of x has a slant or oblique asymptote. Doing long division, the equation can be rewritten as r of x equals ax plus b plus r of x divided by q of x. Note that ax plus b is the equation of a line that gives us the slant asymptote. Sketch the graph of f of x equals x squared plus x minus 2, quantity divided by x minus 2. Let's observe that the degree of the numerator is higher than the degree of the denominator, so we know that there are no horizontal asymptotes. Now let's see if there are some common factors. We'll factor the numerator, which will give us x plus 2 times x minus 1. The denominator is x minus 2, so there are no common factors. Then we can conclude that we have a vertical asymptote, and that is the line x equals 2. Let's mark that. Let's now find the x-intercept. The x-intercept is where y equals 0, and so we're going to set 0 equal to only the numerator. Again, when a fraction equals 0, only the numerator can equal 0. So we've got 0 is equal to the product of x plus 2 times x minus 1. Solving for each of those factors set equal to 0, we get that the x-intercept is negative 2, 0, and the other one is 1, 0. Let's mark those. And now let's find the y-intercept. The y-intercept is what we get when you set x equal to 0, putting in 0 for every place there's an x in the original. I've got 0 plus 0 minus 2 divided by 0 minus 2. Negative 2 over negative 2 is 1, and I get the y-intercept of 0, 1. Let's mark those, or mark it. Continuing. Now, we know there's no horizontal asymptote. We found one vertical asymptote. This is a very special form of a rational function. That is, the degree of the numerator is bigger than the degree of the denominator by exactly 1. And that tells us we have a slant asymptote. To get the equation of the slant asymptote, we're going to perform long division for x squared plus x minus 2. And we're going to divide that by x minus 2. Okay? So we're going to multiply the x in the divisor by an x in the quotient. That will give us x squared minus 2x, and then subtract. X squared minus x squared makes it go away. X minus negative 2x would be x plus 2x, so that's positive 3x, and we bring down the remaining 2. We need to multiply the x of the divisor by a factor. That'll give us 3x. So we will multiply that by positive 3. So 3 times x is 3x. And then 3 times negative 2 is negative 6. We need to subtract that also. So I've got negative 2 minus negative, which would be negative 2 plus 6. That's a 4. Now let's write this. And using division algorithm, we get that the quotient is x plus 3. And the remainder is going to be plus 4 divided by x minus 2. Let's observe the x plus 3 gives us the slant asymptote. The equation y equals x plus 3 gives us the slant asymptote. That's a y-intercept at 3 and a slope of 1. Let's draw that. The x-intercepts and the one y-intercept give us a general guide on the shape of the graph, and connecting them within the confines of the asymptotes, we get a shape that looks like a stretched out funky parabola. Now we need to select some points to see the shape of the graph on the right side of the vertical asymptote x equals 2. I'm choosing x equals 3. And so we will evaluate that in the function. That would give us 3 plus 2 times 3 minus 1 divided by 3 minus 2. 3 plus 2 is 5 times 3 minus 1 is 2 divided by 1. So that's 10. So we have the ordered pair 3, 10. Let's plot that point. Let's try 4. At 4, x equals 4, we will have 4 plus 2 times 4 minus 1 divided by 4 minus 2. 4 plus 2 is 6 times 4 minus 1 is 3 divided by 2. So 18 divided by 2 is 9. So that ordered pair would be 4, 9. Let's plot 4, 9. And I'll try, how about x equals 6? So we'll have 6 plus 2 times 6 minus 1 divided by 6 minus 2. So that's 8 times 5 divided by 4. 40 divided by 4 is 10. So we have an ordered pair 6, 10, 6, 10. And now we can connect these points within the confines of our asymptote, and that's the general shape of our graph. Think about it. Find an equation for the following graph. This graph is in 3 pieces and it has 3 different asymptotes. We have a vertical asymptote at x equals -2, and also at x equals 3. We have a horizontal asymptote at y equals -2. Now, looking at it further, you'll notice or observe 2 x-intercepts, one at x equals -1 and another one at x equals 2. Those are my suggestions for you to get started working on this. Have fun!